Speaking of employment oddities, I have a student who was going to get laid off from Bank of America, but he went on disability right before that. So he's still officially an employee. He doesn't get paid, but still an employee, so he gets like employee discount on some stuff. But if he ever went back, basically stopped his disability, he would be fired immediately.
Yep.
Just thought of a bizarre situation.
So like he can't even go back in? Like
No, I mean, he can't finish out the paperwork saying he's ready to come back. Unless he wants to officially be fired. Or laid off, released, dehired, whatever the word is nowadays.
Position eliminated.
I hope it's not that extreme, but I haven't seen him for a few years, so maybe. That one. All right, so let's start out with Maxwell's equations. There we go. That's what I want. Actually, before we do that, let's just do a quick review. If I have P equals sine of Q, if I did the slope of P with respect to Q, what would that be? In other words, if I took a sine curve, that one cycle looks like that, where that's 2 pi, if this is Q and P. 1, -1. What would the slope of a sine curve look like?
Cosine.
And if you've forgotten that, notice that we have a positive slope here, starts out steep, one of those. Starts out large slope, and then it hits 0, then it's at its maximum negative, and then shoots back up, and that's a cosine curve.
Also known as the derivative of sine.
Indeed. If we did the slope of the cosine curve, what would we get?
Negative sine.
And again, looking at the slope, we start out with a low slope of around 0, then it becomes negative, and then badly drawn because I just wasn't trained to draw it with an extended arm out like that. And if I took the slope of the negative sine curve, if I took a slope of negative cosine, then we'll move back up here. So no matter where we start, we'll end up, it's a cycle. Notation-wise, this is just notation for if I'm doing the slope of delta P over delta Q over delta Q. So if I'm doing the slope of the slope, this would be, it's a clunkier way of writing it. This is the sort of the shorthand. It's not Q squared, it's delta Q squared in a sense. And then this would be delta Q P over delta Q.
Is that the same thing as like P prime with two symbols?
Yeah, so in that notation, P prime, P double prime, P triple prime. All right, I know we talked about that in here before. The next part we did as well, but probably not in as much detail. So let's change it around a little bit, just because this will come in handy for the next star-studded derivation I'm going to do. Because again, Maxwell, why does he get a set of equations named after him when he contributed one term? If I have P is equal to the sine of 2Q, what does that 2 do?
Stretched out. Or is it compressive?
One or the other.
Compressive.
Indeed. If you think about this as sort of the angular frequency, it means, which is very much like the angular speed of the arrow zipping around, it's going twice as fast, and so it'll complete the cycle in half the time in that analogy. And so if this is 2 pi right here, then my curve goes something like that. That is not right. So that'd be pi. There we go. At least it's better than it was. So what does that do to the slope?
Compresses it.
So if I take a piece of paper and
Or no, it decreases it.
so if I have a piece of paper like this, so you think about it, I got a slope on those curves, and then I shrink it into less space, what does that do to the steepness?
It's more.
Matter of fact, it's going to double it. And so my slope here is going to be 2 times the cosine of 2q. So whatever number I have here just gets multiplied out front.
Is there 2 2's? Like, is 2 cosine 2q? Or is it just 2 cosine q?
It's 2 cosine 2q. This part right here stays the same as you go through the slopes. It's just a matter of multiplying out. So if I did the slope of the slope, 2 on the line, P delta Q. But you multiply, so it's cosine becomes negative sine. That 2q stays 2q, and then you multiply times whatever you have right here, so this becomes 4.
Multiply what?
You multiply this. Here, there's an implied 1 here. We multiplied
okay.
1 by 2. Now we multiply 2 by 2, and then if we did it again, it'd be negative 8 cosine 2q.
Would it get to 16 and then go back to the sine?
No, the amplitude just gets bigger and bigger and bigger.
Okay.
The cosine sine, that will cycle through, but the coefficient in front will get bigger if this is bigger than 1. All right, here we go. If I have a function here of p is equal to the sine of q, back to what we had over there, what is the wavelength? Yeah. How'd you get that?
That's how long it takes to do 1 cycle.
What's the period?
Oh.
Oh,
2 pi.
Also 2 pi.
That's
Oh, pi.
funky math there.
Would be just pi.
No, what is the period?
60.
What is a period?
Time
Okay, that's part of it.
that it takes to complete one full, like,
Yeah, all right. What's a wavelength?
it's the length from peak to peak.
Okay, or from whatever the starting point after our cycle. It's how far not a wave travels in one period also. So is 2 pi, so again, looking at this over here, is 2 pi the period or the wavelength?
It is the,
It can't really be both.
It can't be both.
I think 2 pi would
It's the
then be
period.
Period.
So you only don't let them influence you.
I think it's gonna be the period.
Why not the wavelength?
Well, I think we could figure out the wavelength some other way.
All right, so let me just say that you're wrong.
Yep.
And that's not just directed at you, or you're right. What tells us whether this is going to be a period or a wavelength?
Us?
No.
Oh, if there's time on the graph, so it's wavelength because there's no unit of time.
What would, so if Q is time, it is a period. what would Q need to be in order for that to be a wavelength?
Just like a
Distance.
length.
Yeah, a distance. So generically, if I have a wave that is moving, we dealt with standing waves in the last semester, we're now dealing with a traveling wave. There is a time component to it, and there is a position component to it. So if I have a wave here that is moving, I have a wave here that's moving, that where an object is, where a point on the curve is, depends upon time and how far away it is. And so a generic equation for a traveling wave has to involve wavelength and period, or distance and time. And so and by the way, I asked the same question to calculus students at this point, and the calculus-based physics, and they get stumped also. And I think back in math class, when I was going over this and the teacher would ask, what's the wavelength of the curve or the period in math class? And there was never any confusion because it was always, he never threw in a trick question. And so, but now we're at the point where it does matter. So y is equal to some amplitude times cosine or sine of kx minus omega t. So we have these two different parts to it. Omega stands for?
Angular frequency.
Yep. And the period is going to be 2 pi over omega. So this is angular frequency. The wavelength, what would you guess is the wavelength?
Okay. Or
2 pi over omega.
If you combine your two answers.
2 pi omega.
What's inside the?
All right, wavelength deals with distance. X representing a distance.
so K would be KX minus W.
Wow, we're getting way complicated here. So when I wanted to find period, I went to the time term and I did 2 pi divided by that coefficient.
2 pi over k.
2 pi over k, there we go.
We got there.
Yeah. K is known as the wave number.
Oh, yeah. Wait.
Angular frequency is the number of waves per second, or cycles per second, and I guess radians per second. Radians per second, and K is basically the number of waves per length. If I got a meter, how many waves do I fit inside that meter? So if I wanted to find the speed of this wave, so again, it's a traveling wave, whether it's a water wave or a light wave, as we'll get to, electromagnetic wave, whatever that wave is, I know speed is distance over time. We're assuming no acceleration. The distance, well, if I think about one cycle being created, the distance it would travel would be a wavelength, and the time would be a period. So the speed of a wave is just the wavelength divided by the period. Now, we dealt with that before in a slightly different form, because period is 1 over frequency. Speed is wavelength times frequency. That is a different form of the same equation. I know the wavelength is 2 pi over k, divided by the period, which is 2 pi over omega, which is 2 pi over k times omega over 2 pi. So whatever the wave is, the speed of the wave, assuming that there's no dampening to it, the speed of the wave is just going to be omega divided by k. So the angular frequency divided by the wave number is the speed of the wave. That is something that we will exploit in just a moment. And we'll probably go to another board by then, but I'm just gonna write up here, V speed is equal to the annual frequency over the wave number. Questions to hear?
Is that I under the frequency? Yeah.
It's, yeah, because I'm dividing by this fraction, the same as multiplying by
Yeah.
the reciprocal, so it's a mega over 2 pi.
He was coming through your head, right?
Yeah, I know. It will be reflected in his final grade.
I'm sorry, I'm blind.
Can't believe anyone. Again, I did write neatly when I taught elementary school.
You're teaching kindergarten's physics?
Was that?
You were teaching kindergartners physics?
I did throw a little bit of physics in there.
What was you teaching?
I was an elementary school teacher, you teach a little bit of everything.
Yeah, you teach all the subjects.
That's right.
But in the end, he taught me. Got it. As much as I have fond memories of it, I might be hard to believe, but I wasn't really suited for teaching elementary school.
I don't know.
Did they not pick up the sarcasm and the facial expressions as well?
I think I toned down the sarcasm during that time. But if I ever tell a Max story, Max was one of my students. God, that kid was brilliant. He was a second grader reading at a high school level. But he was bouncing all over the walls. 10 minutes a day, he would show how brilliant he was. And the rest of the time, he was bouncing all over the walls. He's probably about your age, maybe a little bit older. It's been a while. All right, so anyway, I digress. Maxwell's equations. We have, if you add up the electric field dot area over an entire surface, that should be equal to the charge that's enclosed over epsilon, so not, we're assuming free space right now. This first bit right here is the electric flux through a closed surface. And that is Gauss's law of electricity.
What is that beside the Q?
Beside the Q right there, E and C for enclosed. It's the charge that's inside that, whatever the surface is.
We decide that, right?
Pardon?
We decide that, right? Like for example, on the test 1A, there was like a Gaussian sphere.
Gaussian.
A Gaussian sphere. It's just the,
It's a virtual sphere. You sort of imagine the surface.
okay, and that's what we mean by enclosed, is that it's these charges inside this imaginary.
Yes.
Okay.
It could be real or imaginary, but
They're just enclosed.
yeah.
They can't be.
What does the ECS stand for on
That's the electric flux and closed surface. Also represented by the circle I wrote in the summation sign. That's what that is. If you've had calculus, this bit right here is also written as the integral with the circle E dot dA. If you have not had calculus, don't worry about it. But later on, when you have it, you go, I did that years ago. Right. So Gauss's law of electricity. Although it might not look like it, this is also Coulomb's law. This is just, take Coulomb's law, which was the first equation we started with, and you just, based upon math and definitions, you end up with this.
after about 500 years?
What's that?
After about 500 years.
Yeah, something like that. All right, next thing, we have the magnetic flux through a closed surface. So we're just gonna do the sum through some closed surface. Not E, V dot A, and that's equal to 0. And the reason why it's not equal to, why it is zero and not something else is this is classical physics, and you can't have just a north pole or a south pole, like you can have a positive charge or a negative charge. So every north has a south, so any closed surface, I have just as many magnetic field lines going in as coming out.
Which means
It ends up being zero. The connection between the flux and how much goes in and goes out is known as the divergence theorem, which some of you will eventually get to. I think that's Calc 3. Then we have Ampere's law with Maxwell's correction, or Ampere-Maxwell's law, where we do the sum of V dot L around an enclosed, a complete loop is equal to U naught times the current that goes through the loop. So if I have a hoop right here, it's the current that goes through it, plus mu naught epsilon naught change in the electric flux over the change in time.
What does that mu stand for?
This mu right here is the permeability of free space. That's the 4 pi times 10 to the negative 7th decimeters per ampere. And epsilon sub naught here is the permittivity of free space. This epsilon is
that's the 9 times 10 to the 9th.
that's related to that. It's 8.85 times 10 to the negative 12 coulomb squared per meter squared.
And then the mu sub naught was
Permeability of free space, that's 4 pi times 10 to the negative 7th.
Wait, what was 9 times 10 to the 9?
That was Coulomb's constant. So, case of E or case of C, like goes back and forth, that's roughly 9 times 10 to the 9 Newton meter squared or Coulomb squared. 1 over K, do it over here, is equal to also 1 over 4 pi epsilon sub naught. So this was the original historical, and it's a lot easier to write, but eventually they connected it with other aspects. And so epsilon sub naught is going to be 1 over 4 pi K, so E or C, whatever letter you're using,
and then it gives you the 8.75 times
8.8